Welcome to Ready to Derive. In this video, we derive the answers to two important limits. The first is this one, and the second is this one. These limits can't be evaluated using the algebraic methods introduced in an earlier video, such as factoring, simplifying complex fractions, and rationalizing. So they call for an alternative approach in which the Squeeze theorem plays a pivotal role. If this theorem doesn't ring a bell, then you should probably watch my video on the Squeeze theorem first. I will link it in the description. Why are these limits so special? Because without them, we would not be able to derive the derivatives, that's a mouthful, of sine and cosine. That fun is saved for a later video. So without further ado, let's get started. So let's think about the first of the two important limits, the limit as x goes to 0 of sine x over x. As always with limits, you should always start by plugging the value in to see if it's one that's easily evaluated. So the sine of 0 is 0, and as x goes to 0, well, this would be 0. And 0 over 0 is indeterminate. So we obviously, it's not something that we can get by direct substitution. And we also see that we can't really use the tools, the algebraic methods that we've learned to evaluate limits because we cannot factor here, we cannot simplify, we cannot rationalize. So we have to find another way. And as a preview, let's just look at a graph of the function sine x over x because it's pretty cool. It's notice that it behaves like sine x in that its period is 2 pi, so it's definitely periodic. But notice that it's kind of what we call dampened harmonic motion. As x goes to infinity, we see that the function gets closer and closer to the x-axis. The x-axis is in fact an asymptote. So it's a pretty cool function just to explore in itself. But the most important thing that we need to see is what exactly is happening as x approaches 0. So from the right, as x approaches 0, we see the function is approaching 1, and from the left. So it's pretty clear that the result we're looking for is to show that this limit is indeed equal to 1. So let's get into the proof of the first limit. I'm going to call up a diagram I borrowed from the internet because it's kind of tough to create, and this is really neat looking and well labeled. So here we go. And we're going to consider, this is going to be a throwback to geometry, and we're going to kind of look at areas and compare their sizes. So let's start with the area of triangle oak. So triangle OAK, is this triangle. And we know, by the way, this is a unit circle. So we know that the base OA is 1. It's a little hard to see there, sorry. This is 1 also. So we know that the area of this triangle would be half the base, which is 1, times the height, which is, in this case, let's go with red, this is KH. So first of all, we have to find KH before we go any further. Now I'm going to introduce an angle. I haven't put an angle in here, but we need that to find KH, so let's call that X. And if we look at this triangle, this little right triangle here, we see that we can use our trig ratios. If we want to find this height, we want to find the value of KH, we would observe, and let's put this on the side, that we see that sine of x is opposite over hypotenuse. So the opposite is KH, and the hypotenuse, okay, unit circle, so that's 1. So the hypotenuse is 1. So therefore KH is just sine x. We can put this in here for the height of the triangle, and we get the area of this yellow region is sine x over 2. Now let's just erase all of that because we want to compare the area of that region to the area of sector oak. Now sector oak is like a slice of pizza. It looks like this. All right, so we want to find the area of this now, and which we know will be slightly bigger than the area of the triangle. So let's put x back in there. And if you recall, for the area of a sector, it's just a piece of the pie. So what fraction of the whole circle would that be? Well, that would be whatever the angle x is over 2 pi. So it would be x over 2 pi. We want that fraction of the complete area of the circle, which is pi r squared. So that would be pi. The radius, once again, is 1. So pi times 1 squared, and we realize that that area will come out to x over 2. So that's the area of sector oak. Now we need a slightly bigger area. So let's look finally at the area of triangle OAL. So OAL looks like this. And we know that the area of a triangle is half base times height. Half the base again is 1. This is the unit circle. And the height, well, the height there is going to be whatever LA is, whatever the value of LA is. So let's call that up. LA, that's once again, remember this is x. So we can use a trig function again. We see that this time the tan of x will equal LA, opposite over adjacent. The adjacent is 1, which tells us that LA is tan x. And then we can go in here. Let's remove LA from there, and let's just put tan x. And the area of that triangle, which is the biggest of all the areas, is tan x over 2. So if we shade that in, we can see that is the biggest of all the areas. And so if we compare the areas and their values, then we get this inequality, which is what we are going to employ in the next slide, along with the squeeze theorem. So continuing with the proof, I'm going to call up the inequality from the previous slide, which actually, remember, the inequality was this, but we can see that we can multiply throughout by 2 without changing the direction of the inequality, and we end up with this for convenience. The next step we're going to do is divide throughout the inequality by sine x. You'll see where this is going in a moment. But bear with me. So we're going to divide by sine x. Now realize that this only stays true, this direction of the inequality of sine x is positive. And it is possible that sine x could be negative if x were in the 4th quadrant, if the angle was like, you know, a negative value. In both cases, the limit as x approaches 0, this would be approaching 0 from the right. This would be the case of x approaching 0 from the left. So it is possible that sine x could be negative, but this, if we were to have used absolute values, that would have throughout, that would preserve the direction of the inequality. But we could do that, and I would have to say absolute value a gazillion times as we're moving through, and then at the end I would just be able to remove it without any complications. So I'm just going to stick to kind of considering that x is positive, and you can assume it would work if x was negative as well. So if we decide to divide through, we would get 1 is less than or equal to x over sine x, right? I'm shaking off the absolute value things now, which is less than or equal to, let's write tan x as sine x over cosine x. And then we can write dividing by sine x as 1 over sine x. So we see that these cancel. And the next thing that we're going to do, let's think of this. Well, let me write this out as 1 is less than or equal to x over sine x. Let me simplify. This is 1 over cosine x. Is we're going to take the reciprocal of this. So we're going to take the reciprocal throughout. And in so doing, we actually do have to change the inequality direction. So take the reciprocal. Notice then in the middle we have sine x over x. And 1 over cosine x would become cosine x. And why you have to change the direction, if you think about it, we know that 1 is less than or equal to 2 is less than or equal to 3. If we take the reciprocal of each of these quantities, notice that the direction has to reverse. Okay, now I'm just going to rearrange this and write this as cosine x, because I like my inequalities going in this direction. It's less than or equal to 1. As you see, we have squeezed sine x over x in between the two functions cosine x and 1. And so it would be true if that holds true for any value of x, then this must hold true, is that the limit as x approaches any value, in particular 0 here, the limit of sine x over x as x approaches 0 must be hemmed in between the two other limits. And it turns out that this is where the squeeze theorem comes in to play. It turns out that this the limit of cosine x, well, as x approaches 0, well, this is just 1. Cosine of 0 is 1. We can plug that in. And of course, as x goes to 0, the limit of this will just be 1, which leaves us with no choice by the squeeze theorem to conclude that the limit as x approaches 0 of sine x of x equals 1. So here we have proved the first of the two important limits. So just to take a sort of another look at this limit, why it makes sense, the limit as x goes to 0 of sine x over x equals 1, I'd like to actually just look at sine x, y equals sine x, and y equals x. So the orange, y1, the orange function is y, the values of y equals sine x, and x is obviously what's in black, the first column. And you can see that look at the value, when x is 0.01, sine of that value, sine of 0.01 is approximately 0.01. And then there's obviously rounding going on here. And you can see that, for example, sine of 0.04 is 0.03999, which rounds to 0.04. So they're very close. So it makes sense that if you think of this, this is just a ratio. The ratio of sine x to x, as when x is close to 0, is 1, or at least it approaches 1. And we can see this also in the graphs. The orange graph, it's sine x, and the black graph is y equals sine x, and you can see that in this region, as x approaches 0, they are virtually indistinguishable, which is just reconfirms that the limit as x goes to 0 of the ratio of those two functions must be equal to 1. Now we can prove the second of the two important limits, which is this limit. Again, this is an important limit because it gets used in proving derivatives of sine and cosine later in the course. But let's just check, once again, always check to make sure you can't plug x equals 0 in. So if x is 0, that would be 0. If x is 0, cosine of x would be 1. 1 minus 1 would be 0 over 0, indeterminate. So we have to find another way. And again, as a preview, let's have a look at a graph of 1 minus cosine x of x. It's pretty cool. Another situation of dampened harmonic motion. So the graph is oscillating like a cosine graph with a period of 2 pi, but it's dampening as x goes to infinity. The function is getting closer and closer to 0. And we can see that we have a hole at x equals 0 because 0 over 0 is indeterminate. And we can also predict that this limit should be equal to 0. And now we're going to prove that. So for the proof of the second important limit, we get to use some nifty little algebraic manipulations to be able to evaluate this limit. So it's pretty cool. And the first one that we employ is to multiply the top and bottom of this by the conjugate. And we have to do something because we realize if we just plugged x equals 0 into the original expression, the 1 minus cosine x over x, we'd get indeterminate form. So we're going to start by multiplying the top and bottom by the conjugate. So 1 minus cosine x. Now just to recall, the conjugate of, say, 1 minus rad 3 is just 1 plus rad 3. The conjugate of 2 plus 5i would be 2 minus 5i. And the great thing about conjugates is when you multiply an expression by its conjugate, and you FOIL, the outer and inner terms cancel, and so you would just be left with 1 minus cosine squared x. So that's one neat algebraic manipulation. So the next one is to recall the Pythagorean identity, which says that cosine squared x plus sine squared x equals 1. Well, why is this important? If we look at the numerator here, we can kind of rearrange this by subtracting cosine squared x from both sides to get this. And so we can replace the numerator with sine squared x. Next clever algebraic manipulation is to write sine squared x as sine x times sine x, and also to separate the factors in the denominator to conveniently get this. Why is that convenient? Because we can sense that we're going to be using a result we just proved. Okay, so the next thing we do is use the law one of the laws of limits that says the limit of a product of two functions, right? So here we have a product. It's just the product of the limits. So we get to write this. We get to separate those two limits out. And we know now from before that this is equal to 1. And here we can just, so it's 1 times, we can actually plug x equals 0 in. Sine of 0 is 0 over 1 plus cosine of 0 is 1. And that comes out to be 0, which delivers us our second important limit, that the limit as x goes to 0 of 1 minus cosine x over x is indeed 0. So we'll end with practicing the application of these two very important limits. So take this limit, for example. It looks very familiar. You might want to think that sine 10x over 10x, that limit would also be 1, but just to make sure we're not doing anything illegal, it's good to make a little substitution and think of, let's come over here and say, well, look, instead of 10x, let's call 10x theta. And then as x goes to 0, that's the same as saying theta goes to 0. And sine 10x would just be sine theta. And 10x would be theta. And so as you might have expected, now we know the limit of this expression. It doesn't matter if the variable is x, if it's a, if it's theta, the answer is 1. So that's very important to realize that whatever's up here must be matched by the quantity down there. So let's try the next one. Now this looks familiar also, 1 minus cosine of x. We know the limit of that is 0. But what about this 4 here? Technically, it shouldn't be there. So for something like this, we would actually factor out the 1/4. And then we would be left with this. And we know the limit of this is 0. It feels probably like we're doing more work than we had to, but just to be, careful. So 1/4 times 0 would be 0. It's important to, extricate any constants in that way. So how about this one? Sine 5x over x. It looks very similar to what we have in part A, except notice that there's a 5 missing from the denominator. So we're going to do a little bit of an algebraic manipulation, and we will, let's see, we need a 5x on the bottom. So we need a 5 there to be able to employ our limits. Well, to get a 5 there, we really have to compensate for that 5 on the denominator by multiplying by 5. So those 5s technically would cancel, but we're kind of introducing them on purpose. And that equals, now I'm going to bring that 5 outside the limit statement because it's a constant, so I can by the laws of limits. We get this, and we know from part A, without going through the motions again, we know that this also will be 1, and so our final answer is 5. Finally, what about something like this? We have to do a little more algebraic manipulation here because we don't know anything about sine 3x and sine 2x alone, but we know that if we could do sine 3x, ideally we would want to divide by x, something like that. So sine 2x, we could divide the top and bottom by x. That's perfectly legal, but that still doesn't help us because we need to get some the factors in there. We need to deal with that 3. So if we introduce a 3 here and compensate for it by multiplying by 3, and introduce a 2 here, compensate for multiplying by 2, in effect we're really not changing the value of the fraction. And then if we bring that 3/2 outside, we can then, the limit of a quotient is just the quotient of the limits, so we can write this over 3x as x goes to 0 all over the limit as x goes to 0 of sine 2x over 2x. And we know that this is just 1, that goes to 1. This is just 1, and our final answer is 3/2. And that brings us to the end of this lesson. I hope you found it helpful, And if you did, please do click like and or subscribe to my YouTube channel, Ready to Derive. Thank you.